define make flip, which of course I don't have the code for. So flip is supposed to do 1 the first time it's called. Let value be 1. And then it's going to return lambda, no arguments. You guys recall this, sort of, right? And the body's going to be right. Well, what am I going to set the bang the value to? Right, we need to alternate 0, 1. You guys wrote this. Come on. Thinking back. 1 minus x. Set bang value minus 1 value. Are we flipping the order here?
No, we don't flip it. That flips it.
Isn't that going to keep going negative?
If you're always subtracting, you have to multiply it by.
No, because it's going to either be 1 minus 0 or to be 1 minus 1. So it's either going to turn out to be 1 or 0, depending on what this was. Right? Okay, so, and then we're going to return value. So we have a couple of choices here. It says it should return 1 the first time it's called. Right now it's going to return 0 the first time it's called, so the easiest thing to do is that. So this is make flip. Let's make this over here our big environment diagram. With this top box being the global environment. And we're defining, so this is, we're defining a procedure, lambda of no parameters with a body of let blah, 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 to the name make flip. So here's make flip, which gets bound in our global environment. We have a procedure object. We're evaluating in the global environment right now. The parameters for this procedure are going to be none. There are no parameters. And the body is let value 0, lambda, no parameters, set bang, value, blah, blah, blah. We're going to run out of room, actually. And this gets bound here. Yes? Cool. So now we're going to define flip 1 to be a make flip. Result of applying make flip. Okay, so we're going to bind flip 1 to the result of that evaluation. So to evaluate make flip, we're applying a procedure, right? We're applying a procedure, therefore we create a new frame. Okay, so that we're all completely consistent in all of our 3 representations, I will use John's notation here. I can use Dimitri's there, and then mine with E1, therefore combining everybody's representations into one.
And you'll chain the arrows together? Someone else had chaining.
Oh yeah, I was doing the chaining of the arrows too. So this point's here, and we can chain these together. Okay. Okay. Those are all the same things, and we're not going to keep doing them. Okay. But somehow you need to know something was created. So in any case, we've created a box because we're applying make flip. It points back to where this arrow points to. Yes?
What's the bare minimum that you would be able to do? Just drawing the box and the arrow?
Drawing the box and the arrow. You don't need anything else. Actually, once you get good at the environment model, you won't do any of that chaining. Because actually, I guess of them all, I like John's the best. John's is writing it above the frame. I like to label the frame because it gives me an evaluation order. And if I need to go back and reconstruct it, I can see in which order I created the frames. But his probably makes the most sense in terms of, because once we start dotting and chaining all over the place here, it's going to get even messier than it's bound to get anyway. So we're making a flip procedure. So we create a frame. There are no parameters to bind. Then we evaluate the body. Okay, it is a let. A let creates a frame. Because there is that hidden lambda. So here we could write let. Chains up to the environment we were in. We bind value to be 0. Create a procedure object. Where are we evaluating this lambda? In this E2. E2, so it points up to E2. What are the parameters to this? And the body is set bang value -1 value return value. That's the body. So this is the result of applying make flip to no arguments. And that is what's going to get bound to flip 1. So there's flip 1. And here's the frame, which is basically storing the state for us for flip 1. This is where the value is stored. So now you're asked to define flip 2. Which is also an application of make flip to no parameters, which is going to look very similar, right? So what we're going to do is we're going to create a frame to apply make flip. Make flip points up to the global environment, so too will this frame. There are no parameters to bind. We have a let. Because of the lambda, implicit lambda, let is going to create a frame when that implicit lambda is applied. And we bind the parameter of that implicit lambda, which is value, which gets bound to 0. Then we evaluate this procedure object. 3. In E4, it has no parameters, and its body is set bang value, and it is bound to flip 2. Okay. So now we've just evaluated 3 things: define make flip, define flip 1, and define flip 2.
How come the E4, the value is 0 and not 1?
Because the body here, it's still the same body, right? So this is 2 separate applications of make flip. And the body make flips is value 0. Okay, so we let it be 0 here, and again we're evaluating it here because it's 0. Okay. And of course, now they change the names of everything on me. So what if we say flip 1? So to do flip 1, if we're applying flip 1 to no arguments, well, flip 1 is this procedure here. To apply it, we need to create a frame, which would be conveniently located perhaps over here. Flip 1 points here, so that frame will be there. So this is flip 1. Okay. There are no parameters, nothing to be bound. Then when we're in this environment, we're going to evaluate set bang value of 1 minus value. So I'm here in E5, and I have no value in this frame. So I look up. There is a value here, and I get 0. So 1 minus 0 is 1. And I'm going to change that to be 1. Then I return the value, which is 1. So this is going to return 1. What if I were to do flip 2? Same thing, except that we're applying this one. So create a frame, which is the evaluation of flip 2. Flip 2 points here, so will this frame. This is the 6th frame that we've created. No parameters. Set bang value to be 1 minus value. No value here. We look up. There's a value. It's 0. 1 minus 0 is 1. Change it to 1 and return the value, which is 1. Okay.
Why do we need E1 and E3? Why do we need E1 and E3?
Why do we need E1 and E3?
Right.
We don't need them, but they are created. Anytime we apply a procedure, we have to create a frame. Even if there are no parameters passed or bound as a result of evaluating that lambda, we need to create that frame.
E1 and E3 ever going to cause any change in the program?
You could write
No environments, I don't know that you can really say that an environment causes anything, and an environment is. An environment is acted upon. It's not the actor.
couldn't you write that meta-circular evaluator to skip that if there's no arguments? And just not extend the environment in that case if there's no arguments?
Sure, we could rewrite our language to not create anything if there were no arguments.
Yeah, you wouldn't do any harm.
It certainly wouldn't do any harm, but we'd have to rewrite the language. A frame is actually created in Scheme when we evaluate it, which is why we represent it here. So actually, now that you guys have seen metacircularity some, maybe the environment diagram makes a little more sense.
Yeah,
Right, because each one of these is a list that John talked to you guys about. So when we're evaluating flip 1 here, our first list is here, and it's attached to this list, attached to this list, attached to that list. Right, and we just chain up, basically cutter down the list until we find a binding that we're looking for. Yeah? Maybe?
Each frame extends the environment.
Right, we extend the environment when we create the new frame. And so the environment gets bigger and bigger. So here, we look up through this stuff here. Here, we look up through this stuff here. So this is basically an empty list, but the environment is represented.
In Scheme. It actually has a physical presence in Scheme.
Yes. Yes, it does have physical presence, which is why we draw it, because it's actually there.
And those frames in the bottom are lost because nothing points to them. So
Right.
it's just got a list without a reference.
Exactly. These frames have nothing pointing to them, so they're just there.
You just can't get them.
Can't get back to them. So in fact, they would be garbage collected at some point. That stuff that's there would be garbage collected away. Well,
Lots of stuff.
yeah, our machines are fast enough that you don't see it. There used to be machines called Lisp machines. They're made by a company called Symbolics. And their machines, you would actually see physically, it would pop up going garbage collecting. And you'd see it, and it would sit and pause and do something. It would be clearing its memory out. Because the machines are so much faster now, you don't see that sort of stuff happening. But it used to be, and it would say, sometimes it would say, you're filling up the memory too quickly, and we're about to go into a slow method of garbage collecting, and it would give you no time to respond. It would tell you this about 20 seconds before it actually did it. And then the machine would be locked up for like the next 4 hours. Yeah. And when it happens at about 12:01, then you're like, okay, this is time to sleep. And you would go sleep for a few hours. It was after midnight anyway. But this doesn't happen anymore. The machines were probably older than that. I mean, I was doing this in 1990, 1991.
Oh, just 10 years ago.
Yeah, just 10 years ago. Yeah. So, but the machines are probably a good 3-4 years older than that.
But not really.
Yeah. Yeah. Yes, sir.
At what point, if any, would flip 1 and flip 2 get garbage collected?
Well,
The whole series of...
we would never, as long as basically the way garbage collection works, and I don't want to go preview the whole, well, I can preview it, but I don't want to go into the whole lecture for garbage collection. The way garbage collection is going to work is that we go through memory and try to figure out what we can get to. And if we can't get to it somehow, we mark it as being something we can't get to, and then we can get rid of it. Right.
How do you know it's there? You cannot get to this thing.
Well, because there actually is physical memory in a computer, right? There's actually some place in the memory, some place in the computer, there's some chip that stores bits, like a memory. You can think of, a disk, a floppy disk stores stuff for you. And what you can do is you can look at your frames, you can look at the global environment and say, what's the stuff I can get to from the global environment? And then you basically make a little mark next to it. And then you basically scan over your memory, and anything that doesn't have a mark over it means you couldn't get to it, and it's clear, it's gone.
Does garbage collection also do some sort of defragmentation?
Depends on what you were doing. If you were actually trying to do some cleaning up like that. There are methods that will do that, and there are methods that don't. We'll talk about that.
But all languages have to have this feature.
I mean, certainly somehow you need to get rid of objects that you're not using anymore. We have a lot of list structure and all sorts of stuff that we do have hanging around more. But yeah, certainly you don't want your memory crowded up with stuff. You can free the memory just by when you come out of maybe in a C function saying, I'm not going to use this anymore. And it's freed up.
You do it explicitly in C, did you say?
No, in C you don't do it explicitly. Well, I mean, you free it up. There actually is a free command. So if you take some space, then you can free it up, and then it can be used later on.
Depends on whether you're doing stack or heap
Right.
allocation. Stack is implicit. You always have to do it explicitly allocation of your host.
What you have to worry about all that, whether it's in the stack, whether it's in the order.
You'll know because you'll do it yourself.
Right. Yeah, if you actually create the memory, you need to free it up. So we'll do garbage collection on Friday. Okay, so we have that. Now we're going to define flap 1 to be an application of flip 1. So here's flip 1 here. We're going to apply flip 1. Unfortunately, running out of board space. So we are now up to E7. And flip 1, this is the procedure object. It points to this frame E2. So we are going to go over there. This also is created by an evaluation, an application of flip 1. There are no parameters. We're over here in this environment evaluating this. And we're going to set bang the value to be a result of 1 minus value. No value here. Chain up. Value. 1 minus value. 0. Then we return value. We return a 0 from this application. So we're going to define flap 1 to be 0. So flap 1 is not bound to be a procedure object at all. It's just the value that got returned. And then
That's not quite what the handout was doing. The handout from 7 was saying flip is the return of make flip. Flap 1 is
right. So rather than so the handout here says define flip to be a make flip, define flap 1 to be an application of flip. But because I didn't want to do another flip because we had already done 2 of them.
okay. But,
So
but by so doing, we're returning 0 instead of 1.
right, because we've already applied it once. It would have been 1 before, right? Right. So we've already applied this once, so it's flipped once. So it's not exactly what the answers that you would have gotten for your homework. It's inverted by 1.
I'm not asking for more frames. I just want to understand.
Yeah, I just didn't. I looked at this and saw that they were defining flip to be a make flip, and we had already done make flip twice. So it didn't feel like doing it a third time was going to help us that much. Okay, so we were going to define flap 2 to be are they giving? Yeah. So this is what they say. Define flap 2 to be flip. And they actually do put the parens around it.
Flip 1 or flip 2?
Oh, flip 1, sorry. Okay, so flap 2 to be flip 1. So let's do this. So flap 2 is defined to be what? What's flap 2? It's a procedure object. Where am I evaluating this? I hear munchkins. Did somebody say munchkins? Okay, create some munchkins. The parameters to this procedure object are what? None. And its body? Right? Application flip 1. And that gets bound to be flap 2. Check. So now, if we apply flap 2, what happens?
Returns the procedure object that's bound to.
Well, let's go through it. We're applying flap 2. Create a frame. Where does flap 2 point to? Okay. Parameters? What are we up to now? E8. No parameters. Our body is to apply flip 1 to no parameters. So we're going to apply flip 1. Where does my arrow point to? I hear E8 and E2. Which one? Okay, we're applying flip 1. Our body is to apply flip 1. Here we don't have a flip 1. We look up here, we find flip 2. We come down here, we're applying this procedure object, and it's pointing to E2. So this needs to point to E2. And I intentionally drew it over here to confuse you, because I'm mean. Okay, so now we have E9. We're evaluating this in that frame. There are no parameters to bind, and I'm here, and I'm going to set bang value. No value here. Follow my chain. Value is 0. 1 minus 0 is 1, and I return value. So I return 1. So an application of flap 2 is 1. Now, when I apply flip 1 again, I've affected, right? Because I defined flap 2 in terms of flip 1, my next call to flip 1 will be something that I may not expect. Because our last call to flip 1 was a 1, but our next call to flip 1 will also return a 1. Because this application, because flap 2 is effectively changing this value here, state. Yeah. And that's where these diagrams start to become really powerful. This would be something that would be incredibly difficult, if not impossible, to represent in the substitution model. Questions? Should I continue along this line, or should I do the one from the exam?
Can you just trace why?
Okay, let's do a flip 1 again. Okay, flip 1 is this procedure object here, and I want to apply it. So let's create frame E10, which is going to point over there. No parameters to bind. I'm going to set bang the value. I have no value here. I'll follow my chain up. It's here. I'm going to subtract 1 from it, changing that to 0, and I return 0. Oh, we had already changed it once before, hadn't we? Yeah. Okay. Return 0. That's where it returned 1 in here. And here it went back to 0. Yes? So we're affecting this one value here. So this starts to look like the environment diagrams of the game. And it starts to get really, really complicated, right? So going out.
So nothing is connected to E8, I guess. It's just walking in.
Right. So E8 was a frame that we created because we were applying flap 2. So we created the frame, got bound here, but there were no parameters to bind, and its body was an application of flip 1, which is why we created E9. But because we're applying this procedure, E9 has to point to where that procedure, flip 1, pointed to. Right? So just very mechanical rules that if I create a frame to apply a procedure object, my new frame points to where my procedure object points to. You don't look convinced. Okay.
That's the basic rule.
Yeah, just rules. And because, I mean, it has to be rules because Scheme is actually doing this underneath, like you guys saw with the Metacircular Evaluator. Scheme is doing something very similar to what the Metacircular Evaluator is doing. It's creating these environment frames. So Scheme has code that's running it. It's just following rules, just like we are here.
How do people who program in this, like professionally, keep all this in mind? You know, what the local environment is when they evaluate these things?
If it's really hairy, they'll draw out the diagram. If you're coding something particularly hairy, yeah, you'll draw out the diagram. This sort of thing, this flip flap, where you do multiple applications of it through different procedure names, is in some sense an artificial example, right? In a lot of senses, an artificial example. People probably wouldn't be coding something exactly like this, but certainly if it's hairy and they're coding something like this, then you certainly would draw out the diagram.
You could just get lost in a big program.
Right. And in fact, if you're drawing the diagram, people might simplify it to some, may not draw this frame. They may just try to keep track of this frame here. Because once, they're using it to model it, but they know if the frame's just going to go away right away, it's not worth drawing. Yep.
One, that's what Neil was saying. So E9 and E10, according to John's convention, would be labeled like flap 2 and...
Oh, sorry, did I stop doing that?
Okay, I figured...
So this is actually flip 1.
Yeah, and then the other one is... there's flap 2, I think.
No, this can't be flap 2. This has to be flip 1. They're both flip 1.
Okay. How would you, in a big program, so you have all those flip 1s, how would you keep track of them? 'Cause you have-
Keep track of
they're
what?
labeled- They're labeled flip 1, flip 1, flip 1. And if I come back to this 2 weeks from now and I see 3 flip 1s, it'd be...
So you applied E5, E7.
Well, you can follow these numbers to see what order they were applied in. So if you had the code that went with it and you had these frame numbers, that's why I actually like to number my frames, because it gives me this sense of sense of time. Which if you just draw the frames, you have no sense of time, especially since some of my frames I went off this way and some of my frames I came off this way. So even just the ordering of the frames doesn't give us a sense of the time.
If you did both, that would make...
Right. Yeah.
So you can't just look at the code and tell this. It's tough just to pick it up from looking at the code and stuff.
It certainly depends upon your experience. I mean, certainly, if you've done a lot of scheme coding, you can look at stuff and tell what it's going to do.
Pretty easy if you just have one indented program in front of it that it scopes up. But if
Right.
you have all kinds of things.
Right. Yeah, I mean, it just depends on people's level of experience and their comfort with it. And if it's really complicated, they'd probably draw a diagram out. Now, the number of people actually coding in Scheme is probably quite small. But I mean, I have friends writing, search engine in Lisp. So there's certainly stuff being done. Yeah, for flights,
Yeah,
for airlines, yeah.
that's like the natural language.
For the search they're doing, actually, they're getting a lot more power than any of the existing sites out there. See this? I'm giving you a plug. The name of the company is... No, I want stock options, man. They haven't gone public yet.
And Lisp looks just like this, right?
Lisp is very similar. It's not tail recursive.
Is that for the natural language abilities?
Yeah, I mean, basically Lisp just has, because of the Lisp processing, it just makes it more powerful as an AI language, and the people who are writing it were coming out of the AI lab and just went with it.
Does the Lisp they're using have more special forms than this dialect? No?
I don't think so.
Really? This is such a compact little language scheme.
So, okay. Enough plugging the friends. Do you guys want to see any more on this, or should we move on to the one from the exam? Exam. Okay. Do you guys have your exams with you by chance, or no? Here, one does. I'll write the code up on the board. We'll write everything up on the board.
I think for me, it's also helping me to understand these environmental diagrams now that we're working with the Metacircular Evaluator to see how that relatively small chunk of code actually constructs these environmental diagrams. It's pretty cool.
Thank you. I feel all warm and fuzzy inside now. Okay, let me write up the code. Because all of you don't have your exams, right? Okay, let's write it up. I'm going to define make soda to have a name, take parameters name, num in fridge, num in cabinet, sugar, and caffeine. If you want to have fun, ask John how to spell caffeine. So let soda, actually it wasn't corrected on this one, right? Yeah. He did the environment diagram. Yes. Okay, let soda be a list of those 5 things, the name. Actually, can I just write NIF? NIC, sugar, and caffeine. 1, 2, 3. Lambda M. And then we had cond, EQM, name. Would that be to write out all of the code here? Or if we got into enough code that it's okay? Okay. So if we create our environment diagram, global environment. Okay, so let's evaluate make soda. Let's define make soda. So make soda is a name that's going to get bound in our global environment. And what will it be bound to? Procedure object. Where am I evaluating this? And the parameters are? All those things. Yeah, great. Name, num in fridge, num in cabinet, sugar, and caffeine. Yes. And the body is let, blah, blah, blah. Okay. Bound. That's it. That's make soda. Now we're going to define make inventory. Dot sodas. Sodas. Okay, just a brief notice, comment. Why did we not just say define make inventory list? Because then we didn't have a nice convenient procedure object to make you guys point to. This is why we did it this way. Because this way we could actually get a procedure object. Otherwise you'd be pointing to the scheme primitive for list. So this is just an easier way to do it for the environment diagram. Okay, so we have make inventory. And make inventory is bound to be a procedure object pointing here. The parameters are sodas, and the body, sodas. Make inventory is bound to that. Check. So now we're going to define a small inventory. Define a small inventory to be make inventory with 2 items. Make soda, Coke, 20, 30, yes, yes. And make soda, Diet Coke, 15, 17, no, yes. Okay, yes?
I just have a question on that prior line, define make inventory dot code and
Yep.
I guess it just sort of throws me off.
Remember, the dot means that the arguments after are optional.
Okay, but
Because what this says is whatever parameters are passed, make a list of them. So then I'm just going to return the list.
You mean that the
Come back.
No, so with make inventory here, we're calling it, we're passing it two things. We're applying make inventory to two parameters.
Okay.
So these two parameters here will be made into a list, sodas, and then we return that list. The dot is what's making the list for us.
So it's almost like we're naming them. Make soda, the name of the list, there's a list.
This is a procedure that's being applied. This is a procedure that's being applied, and each of these is going to return a procedure object. Right? And those two procedure objects that are returned will be put into a list.
Called soda.
It's called sodas only when we're scoped inside this procedure.
Okay.
And then it will return that. So it will return a pointer to that list. It's not going to return a pointer to the name.
So is that last sodas, is that the list sodas? Or
That's a list. We'll go through. As we do this, you'll see how it comes out in the environment diagram.
Is that dot like a sugared version of something?
No, it's in some sense you can sort of think of it as like a special form of sorts, right? Because anything after the dot will be put into a list. So if make inventory were called with no parameters, sodas would be set to nil, and we would return the empty list here. If there were 2 sodas, we'd have a list of 2 sodas. If there were 4 sodas, we'd have a list of 4 sodas, 5 sodas. And something exactly like this was on the solutions to quiz 2. Right. There were a couple of ways that you could have defined the inventory for books way back on quiz 2 a whole week ago. And you could have either bound it to be list, or you could have done it this way. Okay, so we're going to define a small inventory. So small inventory is going to be bound to whatever is returned from this. But in order to apply make inventory, we need to evaluate these two. So we need to, let's first evaluate this. Make soda, Coke 2030, yes, yes. So we're going to be applying the procedure make soda. Applying a procedure. And here I can write make soda. I can put the parameters here to clue us into as to which call created that. But the parameter is going to be inside here anyway, and it's going to give it away for us anyway. So make soda, the procedure object points here, so I will point here, and there are 5 parameters. Name, num in fridge, num in cabinet, sugar, and caffeine. And we're calling it with the symbol Coke, 20, yes, yes. Okay. So there's the frame that's created. And the body is to let. Let has an implicit lambda, so it's an application. Points up to where we were evaluating in. So we're going to let E2. And here in this let, we're going to let soda. And soda is going to be a list of name, num in fridge, num in cabinet. The soda is going to be bound to a list of 5 items. Where the first is Coke, the second is 20, because we're putting in the list the name, so we look up the name here, goes over. We're here, the num in the fridge, look it up, goes over. 30, yes, yes. Okay. So that's the body of the let. And now we have a lambda. So we're going to create a procedure object. We're evaluating it under frame E2. The parameters are M for message, and the body is our cons for dispatching. So this is the final thing that's returned from make soda. Right? So this is our first make soda. What I'd like to do, since I'm not ready to put that in the list yet, let me just put this here to remember that that's where we're going to go, because we actually don't have anything to point to it yet. That was just the evaluation of make soda. Remember, we've just evaluated make soda. We haven't been able to apply make inventory yet. So we don't have that list. So I'm just going to put a little star there to remember that that's where what was returned, my return value. Yep.
Why don't you apply make soda before you define a small inventory?
Because I can't bind small inventory to anything yet, because I don't have something to bind it to. I could write the name up in the environment, but I don't have anything to draw the arrow to yet. And similarly, I don't have anything that I can apply make inventory to until I evaluate these arguments. So that was the first one. So that's my star for the first. And now we're going to evaluate make soda on the Diet Coke. So we're evaluating make soda again. Frame E3, make soda. This procedure object points up to the global environment. And we need to bind some parameters. Name, num in fridge, num in cabinet, sugar and caffeine. So the name is Diet Coke. Num in fridge is 15, 17. No, yes. Okay. So now we bound the parameters. The body is to the let. So let's create another frame, which will be our let. It's going to point over here. I ran out of a little bit of board space here, so I had to move over to the side. So here's the let, and the parameters to be bound within, well, my let frame are soda. And soda is bound to be a list of 5 objects, which if I planned my space a little bit better, I'd be better off. And put that down here. 1, 2, 3. With the first being Diet Coke, 15, 17, no, yes. And then I return soda, well, no, haven't got there yet, sorry. We need to evaluate the lambda. So that's the let, then we have a lambda. With the parameter message and the body, which is the cond. And this here, which we can draw as an asterisk, is what's going to be returned from this. Now, I can apply make inventory to those 2 things that I've evaluated. So I'm going to apply make inventory, creating frame number E5. Make inventory is this procedure object here. Points to the global environment. It has 1 parameter, sodas. So, looking back here, its parameter is the dotted notation, which means it's going to make a list of its 2 arguments here. If it was 3, it would make a list of 3 things. If it was 4, it would make a list of 4 things. So sodas is going to be a list of 2 things, with the first being star. And the second being asterisk. And then we return sodas, which is finally where we get to bind small inventory to sodas. Well, it gets bound to what sodas is bound to. Sodas is bound to this list, so we point to the list. You want me to read something? Or?
Yeah, that's fine. Printing's getting a little small on the far side.
Yep. And that's it. Yes?
So we know that the DA operator before the arguments
Mm-hmm.
doesn't just, is this correct? It it doesn't just mean the arguments are optional, but it means it's forming the list.
It creates a list of the optional arguments.
Okay.
Right. Because it has to do something with them. Because it's only got one name, and it might have 0, 1, 2, 5, 10. So what it does is it makes it into a list. And that's why, if you recall, in some of the problem sets, we've had to use apply. Because we get our arguments in as a list, and we had to use apply to put the procedure over that list. Yep, to break it back out.
Okay.
So this is what's making the list.
Okay.
So if we look at the partial environment diagram, now we can just, they're all labeled different things. Actually, now that you guys understand it, you could reconstruct the exam. The only thing about grading on the exam is there were some dependencies. So these two procedures here and this one could have been swapped. But depending on whether, so one of these was P2 and one was P1. But depending on which ones you had written, which slot, it would actually matter which frame you were pointing it to. Because you had to point it out. If you said that P1 was the first one, then you would better point to the environment that has Coke in it. If you had said P2 was the first one, then it had to point to the environment that had Coke in it. So there was a slight dependency there. So you guys have any more questions on environment diagrams?
Just on the format of the question, I found it confusing just initially to read it and everything like this label, you know, like E4 and arbitrarily assigned. It just like set me back.
Right, we have the object numbers have no relation to the order in which they were created, yeah.
Just like just a while to get
Yeah.
over that.
I noticed when I was taking some of the practice exams, and this really helped me a lot on this exam, was actually to draw out my own diagram, or at least start doing that, and then the rest kind of falls into place, because I think it's really confusing to just look at this and go, oh yeah, okay, this goes.
Yeah, actually, right, it does. 'Cause actually, I designed this question. I broke up those pieces of that, and when I needed to write the solutions to it, it still took me 3 to 4 minutes to look at it to figure out where everything hooked up. And it was a dependency that I was going, I would draw it out.
Put that away and do it, and then
Right, and then you have to coordinate the pieces. I think that's the better way to do it. I think it would be the easier way to do it.
That's what I did in my environment model.
On the
There's
test.
little.
Huh?
I wish you gave us that hint.
Draw your own model, then do it back, yeah.
Big arrows all over the page.
That's one way to do it, too. Yeah.
Or hand out scissors.
Scissors would be cool.
There you go.
hey, just hand us.
Although, I don't know, handing students in the middle of an exam sharp objects. Safety scissors, yeah. Here's some blunt tip scissors. God.
Safety scissors.
So while we're here, actually, I want to make sure that environment diagrams, I mean, environment model is a big thing. Do you guys have any more questions on that? I mean, this is one of the key concepts coming out of this class. Yes?
How did things change when, this isn't really a well thought out question, but when it starts getting object oriented, are there certain things that happen to the environment diagram?
The environment model remains completely the same, whether we're doing object-oriented programming or whether we're doing straight scheme programming. The only thing that was changing is that we had, basically, in the environment, in the game, if you had a procedure object like this let here pointed off to another procedure object.
Right.
That was the inheritance.
So that's kind of the main hallmark of an object-oriented environment.
Usually with object-oriented, you have some notion of inheritance. The message passing, some people would call object-oriented. So if we do any sort of message passing, which we're doing here in this procedure, some people would call messages to get it to do something. But there is no inheritance in this particular type here. So anyway, some object, because it's an object. We're object-oriented right here. We have no inheritance. So you can think of it as object-oriented, or you could have object-oriented with inheritance, which is what we had in the game.
Yeah, okay. And with that one, we ended up having 3 different levels and connecting them with our lets from one level
Right.
to
So
each.
right. So basically, if you had a, we could do one, except I don't have the code in front of me.
Well, that's okay. I mean, that was pretty much giving us the inheritance right there.
Right. So effectively, we would end up if you had some global environment, and we had make object. Rather, make named object, right? And it took in a name, and it had some body. And then we had a make mobile object, And this took in a name and a location, I believe. And then some body. So then the bodies here, this one had a let in it. And this was just returning. It's really hard to do this without the code. But if we were making a mobile object, effectively what would happen is here we would have a named object. In our let, we would get a procedure here that would be bound to say Holly. And then here we would create a frame to apply it. And actually there was another frame in between here, right? And this would be where we would have the name, which would be Holly. Like that. This is really hard to do without the code. When we call Holly here, if we don't find something in the body, then we can chain up here and look over at this procedure object. That's the inheritance coming out. That's how we're inheriting. We have one procedure object. If it doesn't find it, looking up the chain over to something else that's inheriting from. And we could also have another, something else here that pointed to another one like this. So there's this chaining that got us the inheritance. But they were objects like this. They're procedure objects. And then they inherited from other procedure objects.
With something like that, there's always, 2 frames and then the procedures. Is that possible to have any number of frames?
It depends on how we write the code.
Right.
We get a frame when we apply it. We get a frame for let. If we had multiple lets, you could have multiple frames. Right? And actually that's how, if you have a let, we did this example once, so we had let A be 1 and B be 2, and then we tried, B be plus 2A. And then we try to add A and B. If A were scoped in the external environment, it would need to, otherwise we'd get an error. So here, A and B are being bound in the let box, and this can't scope this A. So one way we could write that would be let A be 1, and then do a nested let B be plus 2A. So here we're creating additional frames. All right, so then we have a let pointing to a let frame. So we can write code that will create any number of frames if you'd like. I could write you code that would chain out 8 or 9 frames. You just do some nesting of lets.
Okay, just one last thing. With on problem 1, we had make person, make the object, and make named object. And make named object didn't have a let. And then there was
right, because named object was the simplest thing.
Right. And I'm just wondering if that's necessary, that we go simpler up the chain that way.
Right.
So it was 1 and 2 frames and 3 frames for our most complex the make person, I believe.
Make person should have been a frame for when you bound the person's location and the name. And then it had a let frame to make it for the mobile object that went off to that, and then it was here. The only one that, so most of them should have had 2. I should have 2. The only one that didn't have 2 would have been the named object, because that was basically our base case. That was our ground out there. So we didn't have a let for the named objects. If we got to a named object, the only method a named object has is name. So we get to a named object, we're asking to do anything other than name. It means that that method doesn't exist for the type of thing we were using.
So the base case is going to have no lets. The other ones can have any number of lets depending on.
Effectively, yeah, I guess I would think of it that way. So basically, your most general thing in the model, if it's not going to inherit from anything else, there could be a let for other things, but there's not going to be a let with a procedure object being pointed to, because we're not going to inherit from anything else. That's it. That's the end. So if we drew the inheritance model as diagram for it. Here, we can do object-oriented right now. Ow, 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 ow. So at the top, we had a named object, which had the method name. And it, another class called, not make, but a mobile object. With methods, location, I don't remember off the top of my head, but there were various messages we could pass to it. And then we had a person who was a mobile object with some number of messages that we could pass to it.
Things also.
Things were mobile objects, yes. We had thing here. And I believe that the troll was a type of person. Yep. With its method. Act. In which it crushed Holly and ate her up mercilessly. Poor Holly. And then we also had locations, which were named objects. And then we had ID cards, which were things. Okay. So that's the inheritance diagram for our system that we had.
When a person changes location, where's that tracked? Where do you keep track of that?
There's two things, actually, which is why we need to do a make and install. Because the person needs to have their location in their chain updated, right? So the person has some let state that keeps track of where they are. That needs to be changed. But we also need to change at the location their list of what's there, the list for the location of what's there. So that's why when we ask the location what they see, what it sees, it's going to look at that list of things in the location. This is an environment diagram, so it's sort of weird to talk about pointing like that. But basically, the location has a list of things there. So when you say, what do you see? You'll say, I see problem set, chalk, blah, 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 blah. So the location needs to be updated when something moves in or out. And the person or the object that's being moved needs to be updated on moving in or out. Right? Because a thing needs to know where it is. If it's a mobile object, it needs to know where it is. And a location needs to know what's there. So those are two things that have to be updated if something's moved. That's why we did a make and install person, make and install ID card, make and install mobile object. Because that install is what told the location it was there.
So when this game runs, it just changes the constructions of what's in these lists.
Right. Effectively, there are all these let boxes, right? There's all these frames created by lets that have variables bound inside of them that are being set banged.
Who has what?
Yeah, who has what and where and what. Yep. Exactly. Other questions?